Diffraction in a vacuum chamber. In a large vacuum chamber, monochromatic laser light passes through a narrow slit in a thin aluminum plate and forms a diffraction pattern on a screen that is capital L equals 0.62 meters from the slit. When the aluminum plate has a temperature of initial temperature Ti equals 20 degrees Celsius, the width of the central maximum delta y0 in the diffraction pattern is 2.75 millimeters. What is the change in the width of the central maximum when the temperature of the plate is raised to final temperature Tf equals 520 degrees Celsius? Does the width of the central diffraction maximum increase or decrease when the temperature is increased? So here is our aluminum plate, and we have light coming from this slit with A from this aluminum plate, and you can see that this is going to form a diffraction pattern on a screen that's at a distance capital L away, and we're measuring the width of the central maximum. So these are the points where we will have the destructive interference condition satisfied. Okay, and if I look at Huygens principle, so every point within the slit acts like an independent source of light. So we can see that if I look at the interference of the waves coming from the central point and from the end point here, at a distance a over 2 from the central point, with the approximation that all of these rays are coming at the same angle theta with respect to the horizontal, they are all parallel, and this approximation will hold if the screen is really far away, which is the case in this situation compared to the slit width. It's really, really far away. Now, if we look at the path difference between these two rays, if the angle with respect to the horizontal axis is theta, we can see that this angle, since this is 90 minus theta, will also be theta here. So A over 2 sine theta is the path difference that develops between these two rays. So that's the path difference that's going to develop between these two rays. Okay. So what's the condition for destructive interference? The condition for destructive interference is that the path difference delta between two consecutive rays, which is A over 2 sine theta, must be equal to plus or minus lambda over 2. It should be half a wavelength. So that gives me A sine theta is equal to an integer multiple of wavelengths m lambda, where m is equal to plus or minus 1, plus or minus 2, etc. So how do we obtain this integer m here? So this was the condition we have found using these two, interference between these two. If we consider grouping into the separation between the point sources as a over 4, we obtain another condition. For example, this is going to be a over 4 is sine theta is equal to plus or minus lambda over 2. So that would give us another condition, m is equal to 2 condition, etc. So we can see that we have this, we can recall this condition for destructive interference for the diffraction experiment to be a sine theta equals m lambda. Now, if I look at tangent of the angle theta here, tangent theta, so if this is my angle theta, it's going to form essential maximum here. And if I look at this ray, for example, making an angle theta with respect to the horizontal coming from the center, this is going to be delta y0 over 2 divided by the L, that's the tangent of this angle theta. So I can see that tangent theta will be equal to delta y0 divided by 2L. And for small angle theta, tangent theta is approximately equal to sine theta is approximately equal to theta. And we always define this angle theta with respect to the central axis here. So that's why I'm considering this ray. And the approximation that these two rays are parallel is basically based on the fact that the distance to the screen is much greater than the slit width. Okay, so with that, sine theta is equal to m lambda over a is our diffraction condition, but for the first destructive interference we will have m equals 1, so it's going to be lambda over a. So we will obtain delta y0 over 2L must be equal to tangent theta, which is sine theta, and sine theta is equal to lambda over a for the central maximum. So I obtain the width of the central maximum, delta y0, to be 2 lambda L divided by A. Now what happens to this as the temperature increases? As the temperature increases, I will obtain an expansion in the aluminum plate. The aluminum plate expands, thermal expansion, and when you have an object that goes through thermal expansion with a hole in it, the hole expands the same way as the object. So we find that so does the slit. The slit also is going to expand. And how does it expand? The change in linear dimensions, the width of the slit, will be equal to the coefficient of linear expansion alpha multiplied by the original width and the change in temperature. So final slit width minus initial slit width is equal to alpha A delta T. So we find that the final slit width will be equal to A times 1 plus alpha delta T. So that's going to change the width of the central maximum. Delta y0 prime will be, instead of 2 lambda L over A, 2 lambda L divided by A prime, which is A times 1 plus alpha delta T. So this will be our new slit width. All right, so what happens to the slit width? Well, as the temperature increases, A is going to increase. So we will see that if this A prime is less than A, the width of the central maximum will decrease. All right, so that answers the first question. As temperature increases, the slit width increases, and delta y0, the width of the central maximum, decreases because it goes as 1 over A. Now if you plug in the numbers, the width of the central maximum, delta y0, was initially measured to be 2.75 millimeters. The initial temperature of the aluminum plate was 20 degrees Celsius. Final temperature is 520 degrees Celsius. And we can look up the coefficient of linear expansion for aluminum. It is 2.4 times 10 to minus 5 per degree Celsius. So we have the original central width, 2 lambda L over A, is equal to 2.75 millimeters. Now new central width, central maximum width will be original one multiplied with 1 over 1 plus alpha delta t. So we can calculate this as delta y0 prime is original with 2.75 multiplied by 1 over 1 plus 2.4 10 to minus 5. The change in temperature is 500 degrees Celsius. And this gives us a new central maximum width to be 2.72 millimeters. Okay, so we're looking at the diffraction experiment in vacuum. We use a monochromatic laser light that passes through a narrow slit in a thin aluminum plate and forms a diffraction at a large distance from the slit. And when the aluminum plate has an initial temperature 20 degrees Celsius, we know the initial central maximum width. Now we change the temperature to 520 degrees. What happens to the central diffraction maximum? So first I recalled the condition for destructive interference. If you consider Huygens principle, where I have each point acting as a source of light, and if I look at the interference between these two consecutive rays coming from the center and from the end point here at a distance a over 2, the path difference between these two rays delta is a over 2 sine theta. If that's equal to plus or minus lambda over 2, I have the first destructive interference condition satisfied, which means a sine theta is going to be equal to lambda. So this is the general condition for destructive interference. And for small angle theta, tangent theta, sine theta, and theta are equal. And tangent theta is found by looking at the central axis and at a distance L, the position of the first dark fringe here. So we can see that this angle theta, tangent of this angle theta, is delta y0 over 2 divided by L. And for small angle, that's equal to sine theta. So sine theta is equal to lambda over A. So that's what I substitute here. So this gives me delta y0 to be 2 lambda L over A. As the temperature increases, aluminum plate expands and the slit also expands. So A is going to be A prime, where the change in A will be equal to alpha A delta T. So A prime is A times 1 plus alpha delta T. The new central maximum width is 2 lambda L over A prime, which is A times 1 plus alpha delta T. Since A prime has is greater than A, delta y0 prime is less than delta y0, so it decreases. We can plug in the numbers for the, if we look up the known value of linear coefficient of expansion for aluminum, and we already know the initial and final temperatures and delta y0, we can see that the new delta y0 value is original value times 1 over 1 plus alpha delta t, which gives us 2.72 millimeters instead of the original 2.75 millimeters.